Ready.
I'd like to welcome all of our esteemed colleagues to this presentation for the WISE program here in the summer of 2007. Walter Grosner from Albert Leonard Middle School, New Rochelle, New York. Peter Murphy, Albert Leonard Middle School, New Rochelle, New York. Stephen May, Albert Leonard Middle School, New Rochelle, New York. This is a project that we kind of, at first we had all these visions and we thought we could do this in every way, shape, or form that we wanted to. And it turned out to be a little bit more than we could chew on in this short period of time. But we got it going with what we would like. And basically what it boils down to is we teach middle school, and we're always looking for ways to get the kids super duper involved in everything. And with the use of these sensors added to a simple magnetic levitation project, we decided to run this ramp, and you'll see how it works in a few minutes, but basically what it boils down to is the kids are going to break up into groups of 4. Each team is going to build a magnetic levitation track. Prior to adding the magnets to the track, they're going to run the car down the track so it's a friction-filled environment because the wheels will be running on the track. And they'll record the times and so on and so forth using the sensors device. Once that's complete, then they go into the laws of magnetism and they realize what they have to do to line the track so that the car will levitate. Once the car is in the levitating position, then they can start doing some practice runs. Now, we've premised all of this with them, but basically we gave them a mission. And the mission is simple. Pretend you're in a military zone and the battle's almost over, but you've heard that the enemy is landing a supply vehicle that you have to take out. If you don't take out that vehicle, you've got another God knows how long of battle ahead of you. Your troops are thin, things aren't running right, so the intention is this maglev vehicle that's coming down is going to land in a landing platform. As it lands in the landing platform, based on all the mathematical predictions that we've been taught by our esteemed professors, and the use of vernier calibration equipment, we can determine where that car is going to land, and at the same time, using all of that information, determine where the cannonball coming from the other side is going to impact right on the car and explode it and get rid of it. Again,
Well, we also use the dual force sensor as a landing platform, so we will be getting a force reading on how hard it's hitting that. That would probably be really for a later study if students comparing different cars between groups is what the force is, changing the height of the platform, which we can adjust where the projectile lands. We can also see if that's
change the angle of the track.
There's a lot of variables in here that they can sort of experiment with different readings.
What we did discover was where these photo gates are, you would get a more accurate reading if the photo gates were flat on the x-axis, because now with this angle, you have to take into consideration that there's a resultant force of the x and y axis. But the times that we did it, the change was very minimal, so we're still able to hit the plate without using any vectors. We can just use the straight v sub o sub x that we learned in the projectile motion.
Some of the things, some of the reasons that we even incorporated here, of course, we incorporated the dual range force sensor so that we could use another sensor, but in a real life capacity. Think of,
Okay, so just like the projectile motion experiment that we did, we're gonna run it a series of times so we can get an average velocity, just in case one of them is off, and then with that average velocity, we're going to put it into the formula that we worked out, where we get v sub o sub x, that's the initial velocity before it leaves, is equal to, I'm sorry, delta x, because we want to determine where it's going to land, is equal to v sub o sub x times 2 times the height from the table to the platform, over the acceleration of gravity. Okay, so what we're trying to do is get an average value for the initial velocity in the x direction. And we're doing this all within 60 seconds.
How many we got? One more?
That's enough. Okay, so I'm stopping the data, and then I'm going to statistics. And statistics will give me my average. My mean velocity is 1.319 meters per second. So now we take that
Well, you know what, the height is 14 centimeter difference between the platform and the table.
Edge of the table to the center of the platform.
So move it back a little bit.
No, that's in the right spot, the car fits for.
And, you know, our intention is that eventually it gets to the point with this team of 4, 2 of them are working on that ball coming out of the cannon, and 2 are working on this. And now, based on all of this information, at that point, the cannonball will be released and